going to discuss writing formula of coordination complexes, isomerism, types of isomerisms and various types of structural isomerism, that is linkage isomerism, coordination isomerism, ionization isomerism, solvate or hydrate isomerism and polymerization. So, let us start by writing formula of coordination complexes. The formula of a coordination complex is written in a different order than its name. The chemical symbol of the metal center is written first. The ligands are written next, with anion ligands coming before neutral ligands. If there is more than one anion or neutral ligand, they are written in alphabetical order according to the first letter in their chemical formula. The placement of a ligand in the list does not depend on its charge. Polydentate ligands are also listed alphabetically. In case of abbreviated ligands, the first letter of the abbreviation is used to determine the position of the ligand in the alphabetical order. The formula for the entire coordination entity, whether charged or not, is enclosed in square brackets. When ligands are polyatomic, their formula are enclosed in parentheses. Ligand abbreviations are also enclosed in parentheses. There should be no space between the ligands and the metal within the coordination sphere. In the coordination compound's name, when one of the ions is just an element, the number of the atoms is not indicated with the prefix. Since it still has to be written in the formula, it is determined by balancing the overall charge of the compound. When the formula of a charged coordination entity is to be written without that of the counter ion, the charge is indicated outside the square brackets as a right superscript with the number before the sign. The charge of the cations is balanced by the charge of the anions. For example, if we have to write the formula for tetrafluoridochromium 6 chloride, then it becomes CrF4Cl2. The charge of cation and anion has to be balanced, hence 2 has been written here. There is another example, amine tetraaqua chromium 2 ion. Its formula can be written as CrH2O4NH3 plus 2. As both ligands are neutral, so they are ordered alphabetically with H2O before NH3. Note that their order in the formula is opposite of that the compound's name, since one uses their chemical symbols and other uses the names of the ligands. There is another example in which two types of ligands are there. One is anionic and the other is neutral. Amine sulfato chromium 2. It can be written as CrSO4NH3. As sulfato is an anion, so it comes before NH3. If we have to write the formula of potassium hexacyanoferrate 3, it can be written as K3FeCN6. Note that you have to balance the K. Here 3 comes by balancing cationic and anionic charge. Isomerism is also very important aspect of coordination chemistry. So, we will discuss isomerism now. Isomers are two or more compounds that have the same chemical formula but a different arrangement of atoms. Because of the different arrangement of atoms, they differ in one or more physical chemical properties. Two principal type of isomerisms are known among coordination compounds: structural isomerism and stereoisomerism. Stereoisomerism is also known as spatial isomerism. Each of these isomerisms can be subdivided further. Here you can see isomerism has two types, structural and stereo. Structural isomerism has been subdivided as linkage isomerism, coordination isomerism, ionization isomerism, solvate or hydrate isomerism, polymerization isomerism, and stereoisomerism or spatial isomerism has been subdivided into two types, that is geometrical isomerism and optical isomerism. We will now discuss structural isomerism. Structural isomers, as their name implies, differ in their structure or bond type. This is different from stereoisomers, which differ in where the ligands are attached but still have the same kinds of ligands attached. The notable difference between structural isomers and stereoisomers is that the structural isomers have basically the same chemical formulas but with different bonding arrangements, while stereoisomers have identical chemical formulas. The different chemical formulas in structural isomers are caused either by difference in what ligands are bonded to the central atoms or how the individual ligands are bonded to the central atoms. When determining a structural isomer, we look at ligands that are bonded to the central metal and atom of the ligands attached to the central metal. First type of structural isomerism which we are discussing is linkage isomerism. Linkage isomerism arises in a coordination compound containing ambidentate ligands. These ligands are capable of coordinating in more than one way. The ligands must have more than one donor atom but bind to ion in only one place. For example, the NO2- ion is a ligand that can bind to the central atom through the nitrogen or the oxygen atom but cannot bind to the central atom with both oxygen and nitrogen at once. The formula of the complex is unchanged, but the properties of the complex may differ. The names used to specify the changed ligands are changed as well. The NO2- ion is called nitro when it binds with the nitrogen atom and is called nitrito when it binds with the oxygen atom. Another example is provided by complexes containing the thiocyanate ligand NCS-, which may bind through the nitrogen to give MnCS or through sulfur to give MsCN. When it is attached through sulfur, it is named as thiocyanato, and when it is attached through nitrogen, it is named as isothiocyanato. Jorgensen discovered such behavior in the complex CONH3(5)NO2Cl2, which is obtained as red form in which the nitrite ligand is bound through oxygen, and as the yellow form in which the nitrite ligand is bound through nitrogen. For example, COONO NH3(5)Cl2, that is pentaamine nitrito cobalt 3. In this complex, ONO- ligand is used. In ONO-, oxygen atom donates lone pair of electrons and it is named as nitrito. The same ligand when attached with nitrogen, it comes CONO2 NH3(5)Cl2 and is named as pentaamine nitro cobalt 3 chloride. In this case, nitrogen atom donates lone pair of electrons and the ligand is known as nitro. Hence, these two are linkage isomers. Here you can see the structure of both the isomers. In this case, nitrogen is attached to the metal ion and in other case, oxygen is attached to the metal ion. In ball and stick model also, you can see the difference in the atom of attachment with the metal ion. In this case, nitrogen is attached to the metal ion and the ligand is named as nitro. In this case, oxygen is donating electron pair to the metal ion and this ligand is named as nitrito. If we take the example of hexanitrito N cobaltate and hexanitrito O cobaltate, you can see in first example nitrogen atom donates electrons to cobalt and in second example oxygen atom donates electrons to cobalt. Now we will discuss next type of structural isomerism known as coordination isomerism. Coordination isomers occur with coordination compounds that are composed of both a cation complex and an anion complex, meaning there are two complex ions bound together, one with a negative charge and the other with a positive charge. In coordination isomers, the anion and cation complexes of a coordination compound exchange one or more ligands. Such isomers involve exchange of ligands between cation and anion, that is, between coordination spheres. An example of coordination isomerism is provided here. Hexaamine cobalt 3 hexacyanochromate 3. You can see that 6 amine ligands are coordinated to cobalt and 6 cyanoligands are coordinated to chromium. But in its coordination isomer, that is CrNH3 6 CO CN6, that is hexaamine chromium 3 hexacyanocobaltate 3. 6 amine ligands are coordinated to chromium and 6 cyanoligands are coordinated to cobalt. Hence, these two are coordination isomers. Here is another example for coordination isomerism. You can see these two ligands, that is amine and chloride, are exchanged between these two coordination spheres. Here it is tetraamine zinc 2 tetrachlorido cuprate 2. 4 amine ligands are coordinated to zinc and 4 chloride ligands are coordinated to copper. But in its coordination isomers, 4 amine ligands are coordinated to copper and 4 chloride ligands are coordinated to zinc. In structural formula, you can see tetraamine dichlorido platinum 4 tetrachlorido platinate 2. Here you can see 4 amine ligands and 2 chloride ligands are coordinated to platinum and in another coordination sphere 4 chloride ligands are coordinated to the metal ion platinum. But in its coordination isomers, 4 amine ligands are coordinated to platinum and in other coordination sphere 6 chloride ligands are coordinated with platinum and it is named as tetraamine platinum 2 hexachlorido platinate 4. Let us talk about another type of structural isomerism known as ionization isomerism or ion-ion exchange isomerism. This form of isomerism arises when the counter ion in the complex salt is itself a potential ligand and can displace a ligand which can then become the counter ion. The isomers which form different ions in solution, although they have the same composition, are called ionization isomers. There is exchange of anions between the coordination sphere and ionization sphere. Here is an example for ionization isomers. COBr-NH3 5SO4, which is named as pentaamine bromido cobalt 3 sulfate, and COSO4-NH3 5Br, which is named as pentaamine sulfato cobalt 3 bromide. Here you can see sulfato is present in ionization sphere, and in this complex you can see Br minus is present in ionization sphere. In this isomer, sulfate is in ionization sphere, hence it will give white precipitate of barium sulfate with barium chloride. And in this ionization isomer, Br minus is in ionization sphere, hence it will give light yellow precipitate of silver bromide with silver nitrate. Some other examples of ionization isomers are PtNH3 4 Cl2 Br2 and PtNH3 4 Br2 Cl2. Here you can see bromide is in ionization sphere, but in this isomer chloride is in ionization sphere. In other example, that is PtNH3 4 SO4 OH whole twice and PtNH3 4 OH2 SO4. You can see in first compound hydroxide is in ionization sphere, and in its ionization isomer sulfate is in ionization sphere. In these two isomers, first one has sulfate and second one has NO2 in ionization sphere. Similarly, in this example, first one has bromide and second one has sulfate in ionization sphere. Hence, all these examples contain the isomers which gives different type of ions in solution, and hence these are known as ionization isomers. Here you can see the structures of two ionization isomers, that is pentaamine bromido cobalt 3 sulfate and pentaamine sulfato cobalt 3 bromide. Equimolar solutions of A and B also have different electrical conductivities. The solution A conducts electric current better because its ion have +2 and -2 charges rather than +1 and -1 charges in the solution of B. Because the anion or molecule outside the coordination sphere is different, the chemical properties of these isomers are different. A hydrate isomer is a specific kind of ionization isomer where a water molecule is one of the molecules that exchange places. So, let us discuss hydrate or solvate isomerism here. The form of isomerism is known as hydrate isomerism in case where water is involved as a solvent. This is similar to ionization isomerism. Solvate isomers differ by whether or not a solvent molecule is directly bonded to the metal ion or merely present as free solvent molecules in the crystal lattice. Compounds which have the same composition but differ in the number of water molecules present as ligands and as a free solvent molecule in the crystal lattice are called solvate isomers. An example is provided by the aqua complexes, that is CrH2O6 Cl3, CrH2O5 Cl, Cl2 H2O and CrH2O4 Cl2 Cl 2H2O. You can have a look on this table. there are 3 hydrate isomers. First one is CrH2O6Cl3. All water molecules are in coordination sphere. This is named as hexaequochromium 3 chloride. It is violet in color and there are 3 ionic chlorines. The second isomer is CrH2O5Cl, Cl2H2O. There are 5 H2O molecules in coordination sphere and 1 water molecule is attached outside the coordination sphere. This complex is named as pentaequachloridochromium 3 chloride monohydrate. This is blue-green in color and only 2 ionic chlorines are present. The third hydrate isomer of this complex is CrH2O4Cl2 Cl2H2O. You can see 4 water molecules are present in coordination sphere and 2 water molecules are present outside the coordination sphere. This complex is named as tetraequadichloridochromium 3 chloride dihydrate. This is green in color and only 1 ionic chlorine is present. So, these 3 are hydrate or solvate isomers. You can also see the structures of hydrate isomers. This is hexaequochromium 3 chloride, which is violet in color. You can see 3 chlorides are outside the coordination sphere. Pentaequachloridochromium 3 chloride hydrate. This is blue-green in color. You can see 2 chlorides and 1 water molecules are outside the coordination sphere. And in tetraequadichloridochromium 3 chloride dihydrate, 1 chloride and 2 water molecules are outside the coordination sphere. Hence, these 3 are hydrate or solvate isomers. A very important type of structural isomerism is polymerization isomerism. Compounds whose molecular compositions are multiples of simple stoichiometry are polymers strictly only if they are formed by repetition of the simplest unit. However, the name polymerization isomerism is applied rather loosely to cases where the same stoichiometry is retained, but where the molecular arrangements are different. In coordination chemistry, it is possible to have 2 or more compounds that have the same empirical formula but different molecular weights. For example, CONH3 whole thrice Cl3 consists of 1 cobaltine, 3 ammonia molecules and 3 chloride ions. Other compounds having the same empirical formula are CONH3 whole 5 Cl, CONH3 Cl5 and CONH3 whole 4 Cl2 and CONH3 whole twice Cl4. These compounds are called polymerization isomers of CONH3 whole thrice Cl3, but there is no similarity to the case of polymerization of monomer units that results in a material of higher molecular weight. Now, we will discuss a problem related to isomerism. CuSO4 Cl5NH3 exists in 2 isomeric forms A and B. Isomer A reacts with AgNO3 to give white precipitate but does not react with BaCl2. Isomer B gives white precipitate with BaCl2 but does not react with silver nitrate. Now, answer the following questions. Identify A and B and write their structural formulas. Name the type of isomerism involved and give the IUPAC name of A and B. Now, based on the data given in the problem, we will now discuss its solution. The isomer A is CONH3 whole 5 SO4 Cl. It is so because isomer A gives white precipitate with silver nitrate. As Cl is present in ionization sphere here, hence this isomer will give white precipitate with silver nitrate. And in the problem, it is given that isomer B gives white precipitate with barium chloride. Hence, it is CONH3 whole 5 Cl SO4. Here, sulphate is present in ionization sphere and it will give white precipitate of barium sulphate with barium chloride. As the ligands present in ionization sphere and coordination sphere are different, hence this isomerism is ionization isomerism. Now, we will name these two isomers. Isomer A is named as pentaamine sulfato cobalt 3 chloride and isomer B will be named as pentaamine chlorido cobalt 3 sulfate. And that's all about structural isomerism in coordination compound. In the end of this lecture, let's revise what we have discussed today. Today, we talked about writing formulas of coordination complexes, isomerism, types of isomerism, and different types of structural isomerisms like linkage isomerism, coordination isomerism, ionization isomerism, solvate or hydrate isomerism, and polymerization isomerism.